Good morning, sir.
Hello, good morning, sir. Good morning.
Good morning, Dr. Sahu.
Good morning, sir. Good morning, everyone.
Hello, good morning.
Morning.
Good morning, sir.
Good morning.
Good morning, sir. Good morning.
Hello, good morning.
Sir, promises, sir, we have to join.
You can remind participants also, and
Yes,
we
sir.
should
Yes,
give
sir.
some time to join them.
Yes, sir.
A very good morning to one and all present here. I welcome you all to the AICT Untitled Online Faculty Development Program on Quantum Computation and Information Science, organized by Department of Electrical, Electronics and Communication Engineering, Geetham deemed to be University, Bengaluru campus. It gives me immense pleasure to welcome Professor D.S. Rao sir, Pro Vice Chancellor, Geetham deemed to be University, Bengaluru campus, Professor Dinesh Seth sir, Director, GST, Bengaluru campus, Dr. T.N. Rukmonkathan sir, Head of the Department, Electrical, Electronics and Communication Engineering, Geetham deemed to be University, Dr. Harish Sahu sir, Scientist at Scientific Analysis Group, DRDO, Delhi, for today's inaugural session. I welcome you all, sir. Now I request Professor D.S. Rao sir to speak a few words.
Thank you, Dr. Saranga. Good morning, everyone. My congratulations to Dr. Sunita Panda and her team for organizing this 5-day seminar on quantum computation and information science. I think that the traditional computers, the so-called chip-based computers, have reached their limits now. I think we have been trying to minimize and miniaturize the size of the chip, trying to pack more chips into the same board. I think that has been going on for almost 30, 40 years now. I think this is the time for actually a quantum jump in the computational physics and computational domain. And we are also aware that the DRDO has recently come out with some prototype that has been working on the quantum computing, and we are happy to have Dr. Harish Sahu, sparing his valuable time over almost 2 days to appraise all our participants about the current technology level in quantum computation and how the computation is going to change in the years to come. My congratulations to once again to the EC department, Dr. Rukmongadan, who has been ably guiding his team over the last few years. And our team has been very active in their research. Congratulations to Dr. Dinesh Seth, our director for the School of Technology, and all my esteemed colleagues here and dear participants, and wish you all the very best for the next 5 days of this conference. And I'm sure these deliberations will help you further your research. Thank you very much.
Thank you, sir. Now I request Dr. Dinesh Seth, sir, to speak a few words.
I will remain confined to few words only. Respected Professor Rao, respected Dr. Sahu, subject experts, organizers, and attendees. A very good morning to all of you and a warm welcome for the beginning of a wonderful learning journey. Quantum computing is one of the key priority areas where the attention is currently being given and the efforts are going on, first to focus on train the trainer or train the gurus, and then facilitate the multiplying effect, facilitate the quantum effect when this learning is transferred to the students in the classrooms or trainees and executives in the corporates. And that is where precisely the objective of this FDP comes into picture. The word quantum and quantum computing is not new to us. Before Second World War, some basic work had begun when Max Planck, a German physicist, he first proposed the ideas of quantum and quantum mechanics. Later on, his theory was extended by Albert Einstein, and the majority of the work was confined to physicists. And among Indians, in fact, if we know, then Professor Satyendranath Bose, Dr. Chandrasekhar Venkat Raman, and Professor Meghnad Saha, they were very actively contributing in the areas of quantum physics. For some time, the subject remained dormant. And then a new wave started somewhere around 1980s when Professor Paul Benioff proposed a quantum mechanical model for the Turing machine. So this is how a physics concept was extended into engineering, and that to engineering applications. Somewhere around 1994, Peter Shor developed a quantum algorithm for factoring integers that has a potential to decrypt RSA encrypted communications. And in 2019, Google, partnering with NASA, they claimed that they have come up with a very good quantum computing machine, and that can surpass the conventional computer machines. I'm happy to share this thing that we Indians, we are also actively involved in the quantum computing scale, and one of the key organizations which always makes us proud is DRDO, and DRDO is actively working in the areas of quantum computing also. The strength of quantum computing is using a single machine, you can exercise the computation which can take care of at least 100 or 200 parallel computers. So that is where the strength of parallel computing comes into picture. And what is the outcome? The outcome is that the processing becomes super fast, and whatever type of analysis, whether it is enzyme analysis or chemical analysis or some kind of disease-based analysis, photosynthesis, or development of UFO, development of unmanned aircrafts. So these type of high-end projects can be conveniently addressed through quantum computing. I am hopeful that the participants will be benefited by the expertise of the experts, where they will be sharing the mathematics of quantum computing, physics of the quantum computing, and engineering and applications of the quantum computing. I extend all my wishes to the organizers, particularly Sunita Panda and her team, and I wish good luck for this. Thank you very much.
Thank you, sir. Now I welcome. Now I request Dr. T. N. Rukmakudan, sir, Head of the Department, Electrical, Electronics and Communication Engineering, to speak a few words.
Hello. Good
Hello,
morning to
meeting
everyone.
on the just all right.
Is it okay? There is some audio problem. Hello. Can someone confirm that? Okay. Hello. Good morning.
Audible, sir.
Thank you. Hello. Good morning. And I welcome everyone and wish everyone a very hearty New Year. And it's the right occasion to explore new areas in engineering and based on science. And being a very practical engineer and being curious, I've always felt a bit uncomfortable with the quantum computing. But having said that, I see the potential in it. And let me go back in time and recall what are the developments that have taken place in computing, where one experts give some inputs and expect some reliable output. So that way, the mechanical engineering has played a great role in computing as calculators. I've seen accountants who were, turning some lever and setting some numbers on the wheel, and then there is a mechanical counter which will add or subtract, and multiplication can be done by repeated addition, things like that. I have seen them from a distance. I myself have not operated. But anyway, then came the analog computers, wherein all of us, probably most of you are electronics background, and the operational amplifiers. The very word means that it can do operation like addition, subtraction, integration, etc., multiplication, all these things. And each technology has shown strength and weaknesses. That way, analog computers can solve differential equations. So having said that, you need to have the differential equation. That means model of the system you want to study, and then it instantly gives the solution. And of course, the Turing machine, Alan Turing has done a lot of research, and this proposal holds good. Whether it is quantum computer or the normal computer, what we have today, the Alan Turing algorithm is what works, and it's true. Only thing is, quantum computers promises that it will be faster and many things could be done simultaneously. So once you get into this area, you should be prepared for two jargons. One is superposition and another is entanglement. Okay, so superposition is the first point which we have to get comfortable with, is that the state you got 0 and can in a quantum bit, just like a digital binary bit. You also have quantum bit, and in quantum bit, both states 0 and 1 are simultaneously existing. And then moment you probe it, you only see one state. Okay, so this is one thing we have to get comfortable with, and that is equivalent to don't care conditions in digital logic design. So you can take it as 0 or 1 depending on the situation in a lighter sense. Okay, the other thing is superposition. When you see the superposition, I recall exclusive OR gates. The reason is, they say, this cat business is there. I don't want to repeat. Experts will tell you all these stories. But the point is, when you have two independently linked bits, they are still independent things with the probability assigned to zeros and ones. Still, when you have two of them, one is certain as 1 and another is 0. I don't think I will dwell on this too much for lack of time, but the point is that it excludes two states in our exclusive OR gate. The zero zeros and one ones, and only other two states are the accepted states. And the thing is, the advantage with the quantum computer is going to be like you walk through the maze, and then you can start from one point, try one path. If it doesn't work, go back and start the other path, etc. Whereas quantum computers, because they can exist in multiple positions, the superposition and things like that, it can solve simultaneously and give out the results very quickly. And that is the advantage. Okay. So what I'm going to do is I will quickly finish this, but when I was trying to search this, I also came across two YouTube videos, which I will share with the organizers, and you can see them, and that gives a brief history about the quantum computers and up-to-date progress. The summary of this is that almost about 20 companies are involved, and it is something yet to be seen. As an engineer, I would like to see the computer which works in room temperature. It should be affordable, all conditions, and it should cover less power and things like that. Okay, I also had the fortunate situation where I have worked with the hybrid computers, wherein the digital computer was controlling this thing, analog computer, just to set the parameters, potentiometers, etc. So similarly, the current situation with the quantum computer is that you need a digital computer and you set the inputs and all. I may be a little bit wrong, but experts, you please, if I have done some mistakes, you can explain to them later on. But right now, you need a digital computer to interface with the quantum computer, and you have very stringent conditions to execute any particular process. The advantage is, of course, things can happen simultaneously, and that way it can. And very recently, of course, a Chinese company made a claim that they have a room temperature quantum computer which can solve and all those things, which I am a bit skeptical. But anyway, I think the jury is out, and we will soon know whether it is good or bad. Otherwise, the current status is, although many companies are working, IBM, you can log in and also play with it, the quantum computers. The other part is that Google, along with NASA, what they have is something which is accepted as a quantum computer. Okay, so with this brief, what should I say, my views on quantum computing, I would like to thank the organizers for giving me an opportunity to talk about this. And I will certainly send you two YouTubes, which you can see later on at your leisure. Thank you very much.
Thank you, sir. Now I invite Dr. Harish Sahu, sir, to speak a few words.
Hello. Good morning, Dr. Rao. Good morning, Dr. Seth. Good morning, HOD sir. And good morning, the organizing team and my fellow speaker and the participants. I'm very thankful to the organizing team to organize this kind of event and inviting me to deliver my experience or lectures on some topics. And you feel that quantum is the future. In the near future, you will see lots of quantum computers and communication based on quantum that is secure. So to do research, to motivate young faculty and the speakers, faculty and researcher to pursue this area, I and along with other fellow speaker will try to motivate young faculty and a young researcher to pursue research in this area. So in quantum, you will find that it's not like only computing, it's based on engineering, it's based on mathematics, quantum physics, quantum mechanics. So varied backgrounds researchers are required. So it is the right time for India to start research and motivate participants to pursue this area. And I, along with other fellow speaker, will try to motivate the participant to pursue research in this area. And other agencies like government organization and all R&D institutes are pursuing research in this area. and some of you can get research opportunities in those organizations if you pursue your career in quantum field. Thank you.
Thank you, sir. Today's first session is on Introduction to Quantum Information and Quantum Computing, handling by Dr. Ritabrata Sengupta, Indian Institute of Science, Education and Research, Brahmapur, Odisha. Welcome you, sir.
Thank you very much for this nice introduction. I shall try to share my screen, see that whether it is visible or just a minute, visible or not. If not, I will change a different setup. And yeah, so is my screen is visible as a presentation mode?
Yes, it is visible.
Ah, okay. Thank you very much. Okay, so I should thank the Wittam University for giving me an opportunity. If it were not this COVID
good
like
morning,
lockdowns.
sir.
Yeah, good morning.
Sir, give me 2 minutes time actually.
Okay,
Would
sure.
like to
Sure, madam.
introduce you.
Okay. No problem.
Thank you, sir.
Sorry, sir, I would like to.
No problem.
Participants. Dr. Ritabrata Sengupta completed his PhD in functional analysis aspects of quantum information from Indian Institute of Science, Education and Research, Mohali in 2014. He was a visiting scientist in Indian Statistical Institute, Delhi Center from 2014 to 2016. He joined in Indian Institute of Science, Education and Research, Berhampur in the year 2016 and is working as a faculty in the Department of Mathematical Sciences. I welcome you, sir, for today's session.
Thank you very much for the kind introduction. And I should also thank all of you for inviting me. Well, this gave me a very nice opportunity to interact with you online, though not physically, but I'll try my level best to do it. I should say only one small handicap which I may experience, that I may get a breaking of network connection sometimes. Just in that case, inform me. I may take 5 minutes time to change it to my different network connection. I hope you will excuse me for that. So in this presentation, what I am going to talk about is the basics of quantum computation, and that will be really introductory. However, I am going, at the end of this whole presentation, I am going to say certain things about what are the areas people are working on this at the present, and in the middle also, I will point out certain places which I have not mentioned in the slide, the areas where one can really contribute here. So I joined a little bit late, I am sorry, but when I joined, Professor Dinesh Sheth was giving a very nice lecture, and he mentioned a couple of points which I thought I should talk in this discussion. And thank you, Professor Sheth, for introducing it already. So things are not totally new right now. But let me start with a simple question. Why quantum computation? Okay. So if you just Google it, then you may get a few things about the historical facts about how the quantum computation started. It was quantum mechanics was, of course, long ago it has been proposed, but quantum computation actually started in something in 1976 by Yuri Manin, a Fields medalist from Soviet Union, who proposed this model. But naturally, nobody bothered really at that time One reason was that, of course, he was from Soviet Union. But very frankly speaking, the person who really put his interest in it was Richard Philip Feynman, the great physicist, who claimed that maybe using this quantum mechanics for simulation will make the computer much more faster, because he was bothered with simulation of hundreds of particles, and this work is done naturally in a quantum system. Whereas if you try to simulate it by using a classical computer, it is just extremely painstaking work. And then David Deutsch, Josa, Bennett, Brasha, and various other people started working on it. And then 1996, Peter Shor's famous Shor's factor, 1994, sorry, Shor's factorization algorithm came. And then it became a whole new subject, which is it's still going on. Many people are working on it. Government is giving us money for working on it, and so on and so forth. But I want to ask this question much more academically. Why quantum computation? And I'm not going to give the straightforward answers right now, the things which you generally get in an internet or in a Wikipedia. So first observation is that we all know that the paradigm of computation uses what is called as the Church-Turing thesis. That is, if you can compute, if you want to compute something, if you want to compute it, then there is a Turing machine corresponding to that, and it's a if and only if condition, that is some problem is computable if and only if there is a Turing machine for computing that type of problem. It's not just a single problem. It's not just 2 + 2 = 4. I want to add any two integers, and that's what the algorithm is. And an algorithm can be implemented by using the Turing machine. Here, the first challenge started when this quantum computation came. That these quantum computations are the only model that escapes the limitation of computation imposed by the Church-Turing thesis, and what we require is actually the extended version of the Church-Turing thesis. Of course, this also helps us in a way to use the inherent nature of quantum theory to do certain calculations. For instance, simulating, let's say, 100 particles, how they are interacting with the system, or some kind of a chemical reaction and so on, which happens instantaneously in a test tube, in a lab, or in anywhere. But those things, if you try to simulate it in a computer, you know how much difficult it is. In fact, there are dedicated softwares. They take months for simulating a single chemical reaction or this kind of a physical reaction also. So this is the quantum computation is possibly the only model which escapes the limitation imposed by this Church-Turing thesis, and what we require is an extended version of Church-Turing thesis, or rather say a quantum Turing machine, for really capturing the whole paradigm of the quantum computation. Naturally, of course, you also know the fact that we all are short of ending the practical consequences of the Moore's law, that the doubling of every 18 months is the transistor density on chips, and the resulting increase is in computer speed. And the way things are going on, soon we are going to hit the quantum boundary when we actually have to work on these quantum systems to make to get a much more faster computer. Of course, there are many people in this world who really thinks that there will be difficulties, and yes, there will be difficulties. The scalability is one of the biggest issue in this matter, but still people are working on it, and there are some good progress in this direction. The second thing is the one which I actually mentioned it very first, that it has a profound effect on the cryptography. Probably all of you know that your secure transactions, just the bank transaction, or you have a mobile, you want to transfer some money, get some money, and all these ATM transactions, All these things depends on this cryptography, and this cryptography, many of the cryptographic protocols depends on this factorization, that the belief, that this simple belief that the factorization is a very hard problem. So given a composite number, given a number, to say that whether it's a composite number or prime number, it's more difficult after this Agrawal, Coyle and Saxena's algorithm. But just to factorize a number is pretty difficult. So two very widely used methods in these areas are factorization and discrete logarithm for cryptography. And both these two methods have been broken by the quantum computer, by the source factorization algorithm, and which as a corollary also gives us the discrete logarithm problem. I can also mention one more thing for the online transaction. One more important thing is one more important tool is used as called class number formula. This is a much more deeper thing in number theory. And this class number formula is very difficult. It's believed to be very difficult. Nobody proved it. Nobody knows that whether it is really difficult or not. But it is an extremely difficult problem so far. And the class number formula also, one can find it out by using the quantum computation. So what remains, and this is a very big area right now, that what classical complexity theorists say do is that they try to avoid these problems and try to generalize some sort of a cryptographic protocol which does not use these three widely used paradigms, that is the factorization, discrete logarithm, and the third one is the class number formula. And this is what is called as the post-quantum cryptography. That is something which avoids the possibility that quantum computer can one day break all these kind of systems. The quantum computer science also, people try to do things naturally to break what the cryptographers are trying to make. This is generally like a fighting between two different groups. And well, so far there is not much progress, not much striking progress like factorization algorithm, but there are definitely positive progresses in this. And this is one interesting research problem one can really think of, since many, I have heard that Professor Panda told me that many of you are from computer science background. So this is a very important place to think that another interesting area in which interesting method which is widely used in cryptography is elliptic curve based crypto system. Source factorization algorithm, the methods they use, and the elliptic curve crypto system, the way so far the only way to break it, which is not of course polynomial, otherwise nobody would have used that, uses a good amount of Fourier analysis and Fourier theory. Now, is it the similar kind of thing can be done with the quantum computation also? We don't know, but people are working on it, and I'm sure the computer scientists can make a good progress in that direction as well. So far, so good for the computer science perspective. But there is a good deeper implementation of this of quantum computation upon the fundamentals of quantum mechanics also. So, for instance, the phenomena such as entanglement and the resulting exponential power inherent in quantum physics, and showing that the quantum error correcting codes may be used to bring stability into very seemingly inherently unstable quantum world, has some certain profound uses. And here also something is used for cryptography also. That is, we have also managed to find out certain fundamental aspects of quantum mechanics. For instance, something called Bell's theorem, CGHS inequality, Mermin's inequality, all of them have a to and fro application in the cryptography. So it is not that the computer science only be getting benefited, it's also the quantum mechanics also be getting benefited. And I think some of the physicists will be very angry, but this is also true, because even physicists also tell the same, that okay, can we really make a quantum computer? Can we really make it, or can we not make that thing? This is a question which bothers many people, and whether it is possible to make or it's not possible to make, that has a profound implication in the quantum mechanics, because if it cannot be made, if it is not possible to make it, can you prove that thing mathematically? That means the quantum mechanics may have some inherent bounds which we are yet to find out, such that we cannot really implement these quantum computations. Okay. The fourth point is the last one, that is it has a profound impact on the complexity theory. You all, I think, know about these complexity classes, P, NP, and BPP, and various kind of, there is a complexity zoo also. So many complexity classes are there. Because of this quantum computation, we now have some new alphabets in this complexity zoo, and this gives us certain very important understanding about this inherent the relationship between this inherent relationship between different complexity classes. Okay, so with this I can just ignore what are the things happens in this in the periphery of the thing, and let us just start with a very simple about quantum information or quantum computation. So for that I need a little bit basics on quantum mechanics. Okay, so we need three principles, three basic principles. This is a cheat sheet. I know that all of you are engineers, so you have definitely done some quantum computation, some quantum theory earlier. So I'm just doing a little short way to do it. So the first thing is that the superposition principle. So consider a system with k distinguishable states. For example, the electron in an atom might be either in its ground state, or in the first excited state, or second excited state, or up to k minus 1 excited states. So there are k states are there in which an electron can be, and each of them have progressively higher energy. So as a classical system, we might use the state of the system to store a number between 0 to k minus 1. And the superposition principle says that if a quantum system is allowed to be in any of this number of different states, then it can also be placed in a linear superposition of those states with complex coefficients. That is, that I can have and I can write those systems as kind of a complex linear superpositions, where the complex numbers are given as alpha naught, alpha 1, etc., alpha k minus 1. I need one more condition, that these amplitudes are normalized such that mod of alpha naught square plus mod of alpha 1 square plus up to mod of alpha k minus 1 square is equal to 1. Alpha j belongs to C. And typically this particular electron, in which state it is this electron is written typically in a vector form, and by using the Dirac's bracket notation, this is called kate of psi, which is actually a column vector alpha naught, alpha 1 up to alpha k minus 1. This kate 0, kate 1 up to kate k minus 1, as you can see here, are alpha kate 0, kate 1, etc., kate k minus 1. These are the standard basis. Of course, we will see a bit later that I can take any orthonormal basis. So practically kate 0 means that the first element is 1, the rest of the elements are all zeros. Kate 1 is that the second element is 1, the rest of the elements are all zeros, and so on. This forms an orthonormal basis, and I am just writing this vector with respect to this orthonormal basis, nothing more than that. So at this point, I think it is better that we give a general version of this quantum mechanics, which is useful for my work in particular. So as a mathematician, how do I see quantum theory? So I see a quantum mechanics as a probabilistic theory, but a probabilistic theory which is non-commutative probabilistic theory. So let me elaborate it as slightly more details. In a classical probability space is typically represented by a triplet. It's called as a Kolmogorov triplet. First, you need a sample space that is given by omega, capital Omega. Sample space can be like the following: that you are having a coin, so you are throwing that coin and you are getting a head or tail, so H or T, or maybe G0 and 1, that can be a sample space. Or maybe you have a die and you are just throwing that die, so you are getting between 1 2 3 4 5 6, so it can be a 6, or it can have n number of elements, or it can have infinite number of elements also. Then uh, then the sample space. After that, you have the set of all events. So this is, you can consider it as upon the words upon those sample spaces. For instance, you have a coin, you are tossing it only one, and maybe you are representing head as 1, tail as 0. So you get your events can be only 0 or 1, but you are throwing it twice, your events can be 0 0, that is both tail, 0 1 first tail second head, 1 0 first head second tail, or 1 1 both of them are head. And the last object is a probability distribution based on this sample space and this event space. So the quantum theory is also represented by a triplet, by the same Kolmogorov triplet form. The first thing is that what we require is H is a Hilbert space. This Hilbert space can be of finite dimension or an infinite dimension, and it has to be a complex separable Hilbert space. So for my work, most often what I require in this talk is the Hilbert space should be a complex Hilbert space, C to the power n. This is just like representing the same thing of classical probability, where you require omega can be, let us say, n outcomes are there, 0 1 2 up to n. And similarly, I can have a Hilbert space where there are, it's of dimension n, where the standard basis can be K0, K1 up to Kn minus 1. The second object is the set of all events. This is not too important right now for us. Just for reference, this set of events are the set of all projection operations upon these Hilbert spaces. The most important thing is the analog of this probability distribution in the quantum theory. So the analog of probability distribution in this analog theory is called a state, that is given by the rho, the third entry here. This rho is said to be a state which is number 1 Hermitian. That means rho dagger is equal to rho. Rho dagger means, the notation tells us, is the following. So rho is a matrix. The rho is an n by n matrix. You take the transpose and then complex conjugate of that transpose, you get what is called as the dagger notation. Or mathematicians generally like to use the notation as star, and they call it adjoint. And then the Hermitian is called as the self-adjoint, because then this rho dagger, which is equal to the rho star, which is equal to rho. This matrix rho has to be positive semi-definite. That means the eigenvalues of this matrices should be all greater than equal to 0. And this has to be a trace class operator with trace of rho is equal to 1. That is understandable. This trace is the sum of all diagonal elements, or in the case of the Hermitian operators, you can actually work it out. That is it's the sum of all eigenvalues. This should be equal to 1. Okay. Trace class, the word trace class I have used because your Hilbert space, if it is of infinite dimension, then there is a little bit trouble for trace. But here in this, so what we require is the trace class, so-called the trace class operators. But if you are confining yourself in the finite dimension, then there are lots and lots of things you can do with just in the finite dimension only. And in that case, you have a natural trace, so you don't have to bother too much. Now one can have a thought that what is this state psi ket vector, and what is this rho, which you just now have introduced, what are the relationships between them? So the Kate vector psi represents the rank 1 projection operator rho, which is Kate psi bra psi. Okay, I define the notation bra psi right now, but you can consider it as a psi as a vector, and you are considering the one-dimensional projection operator upon this psi. That is what is the state it will be. And this kind of states where the rank is 1, it's a projection operators, these are called as the pure states. So these psi's are all called as the pure states, and in this case I can write it in terms of a vector because it's a rank 1 matrix practically. So I can write it as a vector. Well, this the state vector is a normalized vector of this Hilbert space, typically written in this bracket notation, and Kate we have already seen. The bra notation is the following: that suppose you have a Kate psi is equal to alpha naught alpha 1 up to alpha n minus 1, the column vector, then the bra psi, which is given here, will be given by a row vector, which is alpha naught bar alpha 1 bar up to alpha n minus 1 bar. The bar represents this complex conjugate of this complex numbers alpha j's. So and this notation came partly because of taking the inner product, which you all know. So Dirac actually broke the inner product in two ways and wrote it as the bra and Kate. So if I have two vectors psi, which is equal to summation of alpha j j, and phi, which is equal to summation of beta j j, where j is some sort of an orthonormal set of vectors, then psi inner product with phi is equal to just a summation over j alpha j bar beta j. This is a standard Hermitian inner product, nothing else. I need one more notions. The notion is on what is called as the tensor product. So what is this tensor product business actually? Remember, in the classical probability, suppose you have a space, probability space or sample space given by omega 1 and a probability distribution given by p1, and you have another sample space omega 2 and the probability distribution given by the p2. How do you write out the joint probability space? It is written in a very simple form, that is omega 1 Cartesian product omega 2 p1 cross p2. It's like two parts. P1 is the first part, P2 is the second part. And generally in the probability theory, it has been always taught that how to write down this joint probability distribution properly. However, so that I must get a similar kind of thing in the Hilbert spaces language also. And in the Hilbert space language, the joint quantum space is given by a tensor product of two Hilbert spaces, H1 tensor H2. Okay, I can ask this question: what is this Hilbert space is about? Consider everything in finite dimension. So H1 you have a orthonormal basis, let us say E1, E2, etc. up to EM. And H2 you have another orthonormal basis, F1, F2 up to Fn. Then H1 tensor H2 can be considered as a Hilbert space where the vectors are spanned by EI tensor Fj upon the same field. Of course, field is the complex numbers for us, so it's not a difficult thing. It's a notation, and you can write it down, the Hilbert space. Well, then what should be the states? Well, the natural question tells us is that, well, it should be something like ρ1 tensor ρ2, where ρ1 is a state in H1 and ρ2 is a state in H2. Yes, it is possible, of course, and there are states, because after all, it's a very valid state. But this is what is called as the classical state, which means not all states in H1 tensor H2 are of the form of ρ1 tensor ρ2. In fact, this is the situation can be even worse, that I may get some states in this H1 tensor H2, which cannot be written as a convex combination of such states. That is summation j is equal to 1 to k, pj, rho 1j, tensor rho 2j. I cannot even write that thing where all these pj's are greater than equal to 0 and summation of pj equal to 1. That is why I use the word the convex combination. If we can write those ways, then these sort of states are in some sense called as the classical state, or in quantum mechanics what we say is that they are called as the separable states. They are just like classical theory of classical mechanics theory. This it is governed by this kind of states. But as I said that there are states which cannot be written in this form. In fact, these are kind of states are called as the entangled states. So I need an example. Consider the system when H1 equal to C2 and H2 is also equal to C2. This is a valid Hilbert space. So you have a C2 tensor C2, which is isomorphic with C4. That means the states will be 4x4 matrices in this C4. Recall from the last slide that what is a slate? What is a state? A state is a positive semi-definite Hermitian operator, trace class of Hermitian operator with trace is equal to 1. So consider this matrix, this 4x4 matrix, where you put 0 everywhere except these 4 corners. Where you put 1, you need to normalize it, so multiply by half. Now this is a state, because this is a pure state also, because I can write it as just a state vector where a column vector which is only consists of 0, 0, 0, 1. And then of course multiply it with so ket psi I can write it as 0, 0, 0, 1, or normalize it by 1 by square root of 2, and then that ket vector can be written in terms of this matrix as like this. So this is a valid state. You can work it out that this cannot be written as a rho 1 tensor rho 2, where rho 1 and rho 2 are states in C2. And not only that, it cannot be written as a convex combination of rho 1 tensor rho 2, some kind of a rho 1j tensor rho 2j. It cannot be written. So this kind of states are called the entangled states. By the way, this state is a very famous state. It is called Bell state. This came from in quantum theory, what is called as a Bell's theorem. To prove this Bell's theorem, this was necessary to construct such states. Also, it is called as the EPR states, because in the name of Einstein, Podolsky, and Rosen, who first conceived this idea of this state, and they thought the following, that existence of these states show that quantum mechanics cannot be true. But much later, Bell proved, Bell actually proved that this because of this, these states are actually not only valid physical objects, but because of their existence, the quantum mechanics is different from the classical mechanics. This is what is, these are states which are called as the entangled states. Here is one problem, and this is a research problem, which is one of the fundamental problem in all this in all this quantum theory, is that some way in every quantum protocol we try to get this kind of exploit this kind of entangled states, and these entangled states are used in a way, these entangled states are used as a resources in the quantum theory. So we need to know whether a state is entangled or separable. Well, this is the most natural thing. I can ask this thing, that whether given a state, can you say that whether it is entangled or separable? Unfortunately, it turned out to be one of the most difficult problems in the quantum theory. In fact, people tried to construct a complexity class to find out what complexity class it belongs to. And it turned out that it belongs to NP-hard. So let me just reiterate the statement. So if you have a given a finite dimensional Hilbert, arbitrary finite dimensional Hilbert space H1 and an arbitrary finite dimensional space H2, take the tensor product of them, which is H1 tensor H2, take an arbitrary state rho in this H1 tensor H2 and declare that whether this state is entangled or separable. This problem is an NP-hard problem. And naturally, it's not very easy to do it, but well, because this type of entangled states are resources, so people actually work on it. In fact, I also worked on it at the time of my PhD. There are lots of industry to find out at least even a small class of such states which are hitherto unknown to us, and just by using certain mathematical tools or developing new mathematical tools. There is again another parallel industry in the physics side or in the technology side, is that whatever the states developed by the mathematicians or physicists or theoretical physicists, let's say, can those states be simulated? Can those states be constructed in laboratory? If it can be constructed, then they can be used for some kind of a protocols. And of course, there is also the moment I use the word protocols, something more needs to be done, because these kind of protocols needs to be find out where exactly they are useful. So there comes the both the theoretical physicists as well as the computer scientists or information theorists who gets new communication protocols or algorithms where they can really use this kind of entangled states. As I said that this is an NP. Oops, extremely sorry. I hope my slides are visible. Hello. Hello.
Yeah, it is visible.
Yes, sir.
Okay. Thank you. Suddenly I just exit this full screen mode. So this is one of the most important problem, and a lot of people are working on it. In fact, I must say that 2/3 of the whole quantum information community works on this the problem. Find out whether this find out a new class of entangled states, exploit it, develop new methods, new algorithms, new protocols where these entangled states have better uses than the hitherto known states, or even naturally whether the even classical protocols naturally. And then the experimentalists, hardcore experimentalists, try to find out in their lab that what is the best way to generate these states. And also the moment, because you have to see it from the experimentalist point of view, so those states has to be very robust, such that they are not perturbed too much by the ambient noise or ambient environment, because otherwise, you are starting with something, you may get totally something else, right? The simplest Hilbert space which you can think of is C2. Okay, so this Hilbert space is obviously this is the smallest quantum space which you can think of. This is called as the quantum bit or qubit. This is in the same spirit that 0 and 1 are the way classical bits by which you build your classical computer. So we try to build everything in terms of these qubits. Of course, we can do it for the other dimensions also, which people work on it, but qubit is the simplest case. You can consider it as a two-level quantum system, just an up or down, something like just up and down or so on, just of a state electron, or you have a suitable system, spin up, let's say spin up, spin down, or a polarization, which may have up polarization, down polarization. So all these qubits, sorry, it should be qubit, is a pure state psi, which is equal to alpha 0 0 alpha plus alpha 1 1, where this 0 is actually the column vector 1 0 and 1 ket 1 is the column vector 0 1. Also, they form the standard basis, the standard orthonormal basis. And naturally, I have to make it as normalized. So mod of alpha 1 square plus mod of alpha 2 square is equal to 1. this n, and this is just a single case. And naturally, you want to, just like in the classical information theory, when you try to build build, let's say, n bit of strings on zeros and ones. Similarly, I also want to make n qubit strings, and n qubit string is given by C2 to C2 tensor power n's. And the typical vector is of the form summation of j is equal to 0 to n minus 1 alpha j j, where this j, this index j is written in the binary form. And when I said that it's in the binary form, it requires a convention. So for instance, I can write it 0 0 0 1 0 0 1 1. They practically means that, let's say 0 0 is equal to 0 get 0 tensor get 0. There's a shorthand way of writing things. So my shorthand is the following, that A tensor B is ket A tensor ket B is can be written as ket of A comma B, or even AB if the whole thing is clear from the process. So okay, so much so for this first thing about the space. The second thing, second important principle about quantum theory is the measurement postulate. Well, now the measurement postulate is actually quite a complicated thing. So what I say is the following. I give a much more diluted version of the measurement postulate. So remember the state psi, which we have taken a few pages earlier. What did it mean? So you have a ket psi, which is equal to j is equal to 0 to k, k minus 1, alpha 0, so alpha j, ket j, or rather I can write it as alpha 0 ket 0, alpha 1 ket 1, plus etc. alpha k minus 1 ket k minus 1. So this is kind of a part of private world of electrons. So the electron can be in any one of these levels, 0, 1 up to k minus 1. I don't know where this electron is at the present. Okay, but I want to know where the electron is by making some kind of a measurement. The two things happens, as you understand. The moment I make a measurement, the electron collapses, the state collapses, and it falls in only one of the systems. So it can be 0, it can be 1, it can be k minus 1, any one of these things. And the probability associated of getting that corresponding jth state is mod of alpha j square. Okay, now this is a little bit complicated thing. So one important aspect of this process is that, as you understand, that it changes the state of the quantum system. So the effect of the measurement is that the new state is exactly the outcome of the measurement. That is, if the outcome of the measurement is j, then the qubit falls down from this linear combination to just the jth thing. The rest of the things are 0, just it is the ket j. Okay, and that means if you cannot collect any additional information about this alpha j by making this measurement, by repeating the measurement. This property actually forms the basis of quantum cryptography, and this sort of prevents the eavesdropper to alter the quantum states being transmitted. We will come to that as a short theorem, sort of pseudo theorem, a bit later. Intuitively, a measurement provides the only way to reaching into the Hilbert space to probe the quantum state vector. In general, it is done by selecting an orthonormal basis. Let's say just like what we have done, 0, 1 up to k minus 1. But if you want, you can take any other orthonormal basis. So that is like E0, E1, E2, etc., ek minus 1. And the outcome of the measurement will be Ej or just j. And the probability associated with that is the probability with the coefficient mod square of the coefficient of that Ej, the ket Ej. So thus the measurement may be regarded as a probabilistic rule for projecting the state vector onto one of the vectors of the orthonormal measurement basis. Okay, and so let me just go back a bit. So consider a qubit. I think this qubit, it became qubit. It shouldn't be the thing. Alpha naught 0 plus alpha 1 1. So measuring 0 psi in the 0 1 basis will give me outcome 0 with probability mod alpha naught square and outcome 1 with probability mod of alpha 1 square, and the state collapses to ket 0 or ket 1 respectively. So it is like, if you can ask this question, that suppose I have this same psi, somehow I have managed to generate the same psi again and again. Are you going to get something more by using this measurement? Yes, you are going to get. You may possibly find out some estimation of this alpha naught square or alpha 1 square, depending on what are the outcomes you are going to get. But you cannot totally get the outcome of this alpha naught alpha 1. But okay, now one question. Cannot we know really about this? What is the alpha naught and alpha 1? Well, you can get fairly a good amount of information also. But for that, you have to do measurement in maybe a different basis. And from there, you have to just come back to the original basis some way. Or you have to do much more, much more intuitive way of doing these measurements. And this is again another area where people work, and also not only the people in the quantum, not only the people like us, but also philosophers also work in this, because the whole measurement principle has several interesting, implementation or implications which comes. For instance, possibly you have heard about the Schrodinger's cat, but you have there are much more complicated paradoxes than that, which comes from the measurement principle. There are also thoughts that whether these measurement principles are complete or not, and also there are ways to think that whether these are the only ways to do measurement, or some different methods are also there for measurement. So there are, in literature, you have something called the weak measurement, Arthur Kelly measurement, and various other kind of, just comes in my mind. These are not like the measurement what we have told here. These are called as a projective measurement or strong measurement in a way. But we really, at the present, we really don't require those kind of measurement processes. But yes, they are there, and they have uses in quantum information theory. Okay, one small exercise you can work out, that consider the same state psi, which is alpha naught 0 plus alpha 1 1, and measure the state in phi, in this basis phi comma phi dagger. That means you consider the vector phi and take the orthonormal vector phi with respect to that is phi dagger, and measure that thing, where my phi is equal to a0 plus b1. Of course, mod of a square plus mod of b square is equal to 1. Well, it's not too difficult, because phi and phi dagger forms another orthonormal set of vectors. So you can write down psi in terms of phi, something like a beta 0 phi plus beta 1 phi dagger. This is just a change in basis which we all do in linear algebra. And then the probability of getting the state phi will be nothing but mod of beta naught square, and the probability of getting phi dagger becomes the mod of beta 1 square. Okay, but if you can work out the simple algebra, it's always entertaining. So let us elaborate this process a little bit more from from these 2 qubit situations. So in the 2 qubit situation, I can ask the question that what happens for let's say what happens for the measurement. Okay, so how I can write the 2 qubits? Well, I can write the 2 qubits in terms of recall that earlier what we have told, that in a single qubit you have a standard basis 0 1. In the 2 qubits, I can write down the standard basis as 0 this basis will be the tensor product of the basis. So there will be 4 orthonormal vectors 0, 0, 0, 1, 1, 0, and 1, 1. And psi can be written as a linear, complex linear combination of these 4 vectors, where the sum of all these mod square entries should be equal to 1. I can consider this 2 qubits. This follows very naturally. You can think it as like 2 electrons in 2 hydrogen atoms, and each of them can be either in the ground state, which is 0, or excited state, which is 1. The second one also is whether it can be the ground state 0, excited state 1, and this is the common thing. And now I can ask the question that what is if I do the measurement on the first qubit only, what I should get? Well, if I make the measurement upon the first qubit, then the probability of getting the qubit is either I can get 0 or I can get 1 upon the first one only. I am asking. So let us consider the case when the first one is 0. That means I have 2 candidates, 0, 0 or 0, 1. That means I get the probability of getting the first qubit 0 is actually mod of alpha 0, 0 square plus mod of alpha 0, 1 square. And the state, what will be the state after this measurement? The state will be, okay, naively I can say that it will be alpha 0, 0, 0 plus alpha 0, 1, 0, 1. But no, the state has to be normalized. So it should be divided by, I am sorry, it should be square root of this quantity. The square root didn't come up. So mod of alpha 0, 0, square root of mod of alpha 0, 0 square plus alpha 0, 1 square. There is a typing mistake here as well. Extremely sorry for that. So this will be the state where it will collapse. Similarly, if I ask this question about what will be the case for which the first qubit is 1, in that case the state will collapse. The probability of getting that will be mod of alpha 1, 0 square plus mod of alpha 1, 1 square, and the state collapse will be just the second part divided by square root of the probability. This is required to normalize the state. Okay. The last postulate in the quantum theory, and which we will use for quantum information, is that unitary operations. So the philosophy here is the following, that any sort of quantum transformations are actually an unitary transformations. So evolution of a quantum mechanical system is guided by the unitary evolution. So if you have an n level of quantum system, then the corresponding unitary evolution is an n by n unitary matrix U. Then such that U dagger U is equal to U dagger is equal to 1. This is the definition of the unitary group actually. Some small properties. So rows and columns of U forms an orthonormal basis, and U is a unitary matrices preserves the inner product. That means if you have 2 vectors x and y, then ux inner product with uy is the same as x inner product with y. So this is kind of the Hermitian way of preserving the length of every vector in a Hermitian space or in a Hilbert space. The eigenvalues of u are of the form e to the power I theta. All the eigenvalues comes in this form, and these matrices U's can be diagonalized further, and the diagonals will become that e to the power I theta 1, e to the power I theta 2, etc. e to the power I theta. A short way of cheat sheet here, when I typically do apply an unitary transformation, I do the following. So this is an unitary, this is a state U, small u, kt small u is going, and this single where actually represents this Hilbert space. In this Hilbert space, I am sending a state ket u, and u is the capital U is the unitary operations. So the output will be upon the where it will be u ket u. This emitter sign actually represents a measurement, and after doing then the measurement outcomes typically are given in terms of 2 lines. This is kind of a standard notation which we are following for many years. Those who are much more from physics background, they may complain the fact that well, not every evolution is given by a unitary, but there is a philosophy here that you may not see the transformation as a unitary right now, or even mathematically also. But if it is a quantum mechanical transformation, then you can extend your Hilbert space, merge it with an environmental system, which can be which may is a little bit higher dimensional, or it can be whatever it is the dimension it may be. But in that bigger Hilbert space, every evolution is an unitary evolution. So this is kind of a philosophy, and it can be proved mathematically also that if you have a quantum mechanical evolution, quantum mechanically transformations, any quantum mechanical transformation will be given by the unitary evolution, except measurement, because measurements are collapsing the system. Okay, these unitaries are also called as the gates. So unitary, this is in the same spirit as in the classical information theory. We have this, you have NOT gate, AND gate, NOR gate, etc. Similarly, we have the gates which are given by these unitary transformations. So let me give some examples of useful unitary operations. The first useful example is the Pauli gates. This is these are these three matrices. The first one is actually very important. It's called the NOT gate, 0, 1, 1, 0. Notice that if I apply it upon the gate 0, then I will get gate 1. And if I apply it upon the gate 1, I will get gate 0. So that is what it is, kind of a quantum NOT gate. The second one is called the Hadamard gate. This is as is given in the matrix 1 by square root of 2, 1, 1, 1, minus 1. And if you want to apply it upon an n qubit system, then you require n-fold tensor products of that, which is whose action is given in the following way, that h tensor power n, x equal to 1 by 2 to the power n minus n by 2, summation y is equal to y is in 0, 1 to the power n, y belongs to, it should be minus 1 to the power x dot y into y, where this x dot y is actually x1, y1 up to xn, yn. Y is written in kind of a binary notation. So it is either 0 or 1. Similarly, x is also written in the binary form, that is either x or either 0 or 1. Now I need some, okay, one more thing is the rotation gate. That is just if you have 0 and 1, you are rotating with respect to an angle theta, and that gives the rotation gate cos theta, sin theta, minus sin theta, cos theta. One very important gate is called the control NOT gate or C NOT gate, whose matrix is actually unitary matrix is given in this following way. And it acts in this manner. So I and j are binary, so it can be 0 or 1. So, and the C naught acts in the following way. I comma j goes to I comma I direct sum j. Direct sum j means that I plus j modulo 2. That means, what does that mean? Is that you have 4 basis vectors 0, 0, 0, 1, 1, 0 or 1, 1. Consider this this notation here. This is generally the way we represent it. The first one, this black dot here is called as the control, and the white one is actually the NOT gate, and they are connected each other by a wire, small wire. This is how we represent the whole thing. The idea is that the first qubit is going through the first wire, the second qubit is going through the second wire. The first qubit, if it is 0, the control will not actually work at all. So 0, it will pass as it is. That's why, so 0, 0 will become 0, 0, 0, 1 becomes 0, 1. But if the first one becomes 1, then this unitary operator here will be activated. Okay. And that means here the NOT gate will be activated. So if this side 1 goes, then this side, if it is 0, then it will become 1. That means if I send total, if I send 1, 0, it will become 1, 1. And similarly, 1 1, if I send, it becomes 1 0, because 1, in that case, first 1 they can see it and it will activate the gate. Where it will see 1, it will convert it to 0. See, that can be written in a very neat form, that is I comma j is equal to I comma I direct sum j, that is I plus j modulo 2. So a similar gate is called as the swap gate. This is also very important operation. Swap gate does the following. So if you have an orthonormal basis and I and j is are there, so it will convert I comma j to j comma I. How it will be? It will be working. So the 0 0, this is the matrix. You can work out yourself that 0 0 will become 0 0, nothing changes. 1 1 remains 1 1, nothing changes. But 0 1 converts to 1 0 and 1 0 converts to 0 1. That is how this matrix is given. I can do it in the same spirit of control NOT gate. I can make a control unitary gate where you have a 0 passing through this, nothing happens, but 1 passing through that, this unitary gate operates. Or I can, in the same spirit, I can have y2. I can build it upon 3 also. So I can have 2 controls, and then the third one is a NOT gate. Or I have a single control. This is a swap operator. That is, everything is possible. You can just play with your pen and paper and can construct new gates actually. This one is called as the Toffoli gate. This one is called as the Fredkin gate. In fact, as Professor Sheth was mentioning, that the existence of this new tool called IBM Quantum Computer is available, and there's a simulating program is available online called IBM Quantum Computer. So you can actually work on this quantum computer. You don't require to pay anything. There is just Google it. You will find out the actual page, and you make an ID and password of that. And there you can just work on, you can make your new gates and pass the different qubits and find out how those qubits are behaving. It's pretty interesting and pretty fascinating. You can in fact, many people actually publish paper based on by using this computation outcomes given by the IBM quantum computer. Most often it happens that you have to find out a problem, and then you have to draw the suitable gates. Rest of the good part of the computation will be done by the quantum computer. The outcomes you get and you write it down neatly, you get a publication. This is generally, many beautiful papers came up in this nice way. In fact, I think India is sort of the topmost countries where this IBM quantum computer computation is used extensively. So much. Other is the Brazil. Okay, I think I now have roughly around 20 minutes or so. So I give a simple, simple algorithm just to conclude the whole quantum introduction. So what is the major problem we have in the quantum theory? We have several such major problems. Of course, the experimentalists, in particular the engineers, know that if you consider a quantum system, then it's very, very difficult to separate it from the environment. And in fact, environment will always degrade the system and it will become something else. So you need robust systems, you need robust methods, you need storage devices and various other kind of things. But these are standard. These are kind of standard processes which comes which goes over with increasing technological achievements. But what is more important is the fundamental part of quantum information is a theorem which is called no cloning theorem. Just I give a short hand-waving proof of this no cloning theorem, but let me motivate you how does it work. Consider the classical information theory. You have some information. It may be in your telephone line, maybe in your mobile or something like a radio wave, some kind of a radio wave, or anything. What you require is, if you can tap that information, you can always copy that thing. You don't need to know that what you are copying. You can copy it. There is no problem in that. Let me be a little bit more frank here. You know, let's say you know about a Xerox machine. So you put a paper which contains something, some kind of a writing, some legal document maybe, and you put a blank paper. The Xerox machine copies everything as it is. So the machine does not need to know what is written in your paper, but it copies. So any unknown document, any unknown information can be copied as many number of times as you want. But in quantum mechanics, you cannot really do it. So the question is the following: that suppose you have an unknown quantum state psi. So is it possible to get an unitary operator U such that U acting upon this psi and something else that may be that zero, ket zero, which I have written, that is just the blank papers like you are pushing in the Xerox machine, and the outcome becomes psi tensor with psi. Just like U is the Xerox machine is possible, unitary Xerox machine is possible such that you have this psi, original psi, and another copy of the psi. Of course, you have to give some resource, that is the extra blank paper, which I write it as 0. Is it possible or not? Well, if it is possible, in that case, why for a single psi? It can work for any object, any state, right? I mean, a Xerox machine doesn't work for only for one document. It works for every kind of documents, right? Any page you just make a copy. So U phi tensor 0 is also should be equal to phi tensor phi. But then you see a single problem happens from this first equation and the second equation. You take phi tensor 0, ket phi bra phi tensor bra 0, you need to take U dagger into U ket psi tensor ket 0. This is just the I am taking a dagger with respect to the second equation. Left and right side, I just use a dagger, so it becomes k bra, and this U dagger becomes this side. U becomes U dagger, comes in the right hand side. Take the inner product with this this object, the previous equation. You get the right hand side, you get inner product of phi comma psi into phi comma psi. Very natural. And what happens in this side? Well, U dagger U is an identity, U is an unitary operator, so U dagger U has to be equal to identity. So that gives us only phi tensor with bra phi tensor with bra 0 into ket psi tensor with ket 0, which can be written as phi phi inner product with psi, and of course 0 inner product with 0, but 0 is a basis vector, orthonormal basis vector, so that is equal to 1. So hence what we get is from this equation is that phi inner product with psi is the same as phi inner product with psi whole square. Now this equation gives us some sort of a trouble, because this equation has only two solutions. That is, either phi inner product of psi is equal to 0, in which case phi and psi are orthonormal to each other, orthogonal to each other, or phi inner product with psi is equal to 1. In that case, they are the same. That means this unitary operator works only for this phi and psi. But what happens if I take a phi dash, a different vector? Well, you cannot really say that you have only two vectors in the whole Hilbert space. It should work for every vector. So that means this unitary operator has a inherent handicap. That is, it cannot work for each and every vectors. That means such an unitary operator does not exist. That universal Xerox machine of unitary does not exist really. Okay. This is what is called as the no cloning theorem. So if I have an unknown quantum state, I cannot have a machine or a machinery such that I can copy that unknown quantum state at all. Okay. In this situation, it may be a little bit surprising if I just point out that there is a way I can say I can transfer an unknown system to somebody else, because I may say that I have the problem that I don't know myself that what state I am going to send. Then what is the thing I am sending? But there is a protocol which is given by the Benedicts and others sometimes in 90s, which is called as a teleportation protocol, which does the following. That suppose I have Alice and Bob. Alice wants to send a state psi to Bob, and they come up with a quantum channel which is given in this way. The diagram is given here. Alice is ready to destroy the her part of the her part of the state, and in that way Alice can generate 2 bits of classical information which she can inform to Bob by sending making a telephone call, and Bob can recreate that state psi. Now that seems like the following, that in the sci-fi movies where some sort of a laser beam falls and something is destroyed, and then at some point of time some different place some laser beam comes and it just generates. So it is something like in the same spirit. So what are the resources required? Of course you need to take psi, which you need to send through the first channel, the first line which is given here. You need a CNOT gate. You need a Hadamard gate, which has been given here. You need 2 pieces of measurements, but more important, what happens in this second and third bits. In this second and third, Alice controls the first one and the second one, and Bob controls the third one. And Alice and Bob together in this second and third line sends what is called as the EPR state or the Bell state. This is the one which I have actually now written in the vector form. You have already seen it in the matrix form, where it was a 4x4 matrix. 4 corners are 1 and normalized by half. This is the same monster here. If you do the calculations, then it becomes the initial state of the system becomes psi naught, where like this is equal to psi of 0 0 plus 1 1 by square root of 2. I can if my psi is equal to alpha 0 plus beta 1, then the whole thing can be written as 1 by square root of 2 alpha 0 0 0 plus 1 1 plus beta 1 into 0 0 plus 1 1. Now the first time the CNOT gate has been applied, what it will happen? So each and every element here will go through the CNOT gate. So when the first object is 0, nothing happens, but the moment the first object is 1, the second bit converts to, if it is 0, it becomes 1, if it is 1, it becomes 0. Then I apply the Hadamard transformation upon the first bit. So a little bit of calculation comes like this. And if I collect the first 2 qubits of the state psi, then the whole thing can be written as the psi 2 as in the following way. Half of 0 0 as alpha 0 beta 1 plus 0 1 alpha 1 beta plus beta 0 plus 1 0 alpha 0 minus beta 1 plus 1 1 alpha 1 minus beta 0. This is nice. Now I can ask the same question, that what happens for if I take measurement on the first 2 bits. Okay, the first 2 bits, that means I can get either 0 here, 0 here, the first one 0, second one 0, first one 0, second one 1, first one 1, second one 0, or the first one or both of them as 1. So there are 4 possible outcomes. But wait, my state will also collapse in those things, right? So each of them are having probability 1, probability half. So if Alice gets the measurement 0 0, then the state collapses to alpha 0 plus beta 1. This is the first one. If it gets 0 1, then the box thing collapses to alpha 1 plus beta 0. 1 0 if it collapses to alpha 0 plus minus beta 1, and 1 1 converts to alpha 1 minus beta 0. Now you can ask this question that, well, I am not getting alpha 0 plus beta 1 except from for the very first situation. My answer is that the Alice measurements, these two classical bits, which he will make a phone call and inform Bob in a classical channel, will give Bob some ideas about what gate has to be used. So if Alice sends this 00, then Bob knows that, okay, I got 00. I don't have to do anything. So that is identity operator. I got my unknown state. I got it. Alice sends 01. Bob says that, okay, I think I got it with a little bit of change. So I have got alpha 1 plus beta 0. If I apply it just X transformation, that is the quantum knot transformation, I get my original thing, because in that case 1 becomes 0, 0 becomes 1. Similarly, 1 0, then I have to transfer what is called as the Pauli gate Z, and 1 1, I have to do a little more X followed by Z transformation. So what is happening is that Alice destroys her system and gets some classical information which is sent to the Bob, and Bob can recreate the state. Now one can ask this question is about, okay, what happens in this thing? I mean, after all, this is a protocol which is like right now something like a 30 years old almost. Well, then many interesting things are still discovered in the teleportation protocol. The first important thing, philosophy you should understand, is that this teleportation protocol gives you a nice way to transfer an unknown quantum state from a sender to receiver without in the middle person knowing anything how it is going. Okay. Or tapping by any other persons, or even to know, or even just you want to send the information by some certain, you want to give some information to Alice. Alice needs to transfer it to Bob, but at the present Alice should not know about the information, what it is, what the information or what the state is actually. Then this teleportation protocol is the best way they can do that thing, because then they can do this protocol any number of times, any number of ways, but Alice would not know anything about the state to be transferred to Bob. So this is always, teleportation protocol is always used as a part of a protocol in cryptographic systems, where some information needs to be transferred, some unknown state needs to be transferred, and where the classical communication is allowed. The second thing is that I am doing this whole calculation for a qubit situation. Of course, naturally one can do it for any arbitrary dimension also, but how much one can do it in particular for infinite dimension, for which you have a Gaussian systems or maybe a non-Gaussian systems also, that is not always very clear. There is a Gaussian teleportation protocol, but there are certain limitations of that protocol. It's not as good as this qubit protocol is. The third thing is that in this whole process, we have ignored one single thing. What if there are some noises in the whole system? Can this teleportation works? Is it possible for the teleportation to work or not? This is an important research area on which many people really worked, and quite a few recent papers came up in this direction. In fact, I am actually at the present writing one paper in this direction also. I never thought that I will be working on teleportation, but yes, now today I am again working on the teleportation. The fourth important thing is that Alice and Bob sends this kind of a Bell state or an entangled state, but there are so many entangled states available. If I send something else, will it be equally good or equally bad or something? I can also send the same kind of things by using a mixed state also. Why I should always think of sending a pure state? Okay, good part is that if you consider just this pure state here as the entangled state resource in the second and third bit, and then this psi, instead of this psi, you can send a mixed state also, you can actually work out the computation, and you can see that this whole teleportation protocol works perfectly without any problem. But what happens if instead of sending a pure state, pure entangled state like 1 by square root of 2, 0, 0 plus 1, 1, if you take a mixed entangled state, will it work or will it not work? This was not known till okay, now 2 years last till up to 2019, when a series of papers came and they showed that yes, this thing is still possible with with any arbitrary entangled states, but the penalty you may have to give is that you get some kind of a probabilistically teleportation will take place. So you may not get exact the same thing, but you with some probability will get it. And the probability one can show, one showed that this protocol can be modified slightly else, some slightly different way, such that this whole thing, the probability of reconstructing the state psi is at least 2/3. That means it is really good, or really high probability is there for doing this thing. Okay, so that gives important quantum protocol, which everybody should know who is doing this quantum information theory. But of course, there are much more important protocols are there. For instance, there is Dwight-Joseph algorithm, which I could have done possibly, but I did not do it. And Simon search algorithm is one such another algorithm. And of course, the Peter Shor's this discrete logarithm, factorization algorithm, discrete logarithm problem, etc. These are also available to us, but that requires a much more longer time to do it. The last thing which I should tell, I should ideally stop here, but the last point which I want to emphasize is that the quantum because of this measurement and the probabilistic nature of this all the protocols, the quantum the complexity of this is of a little different. It is called as the BQP, the bounded quantum probabilistic protocol. So it's the quantum, all the algorithms are actually in BQP domain. That is a quantum protocol where the probabilistic, which is probabilistic in nature, and the probability of success is at least 2/3. That is generally is assumed. The question is that where exactly this bounded BQP is there. That is still not clear. It's as you expect from the problems of complexity theory, that is still not very clear. It is expected that in certain way, this breaks the different complexity paradigms. For instance, it may have some NP problems, but not NP complete problems. It may solve some NP problems. For instance, if factorization one proves that NP, it's not proved to be NP. It's believed that it is NP, but its complexity status is unknown. Then yes, it is possible to break. Then it is, of course, we have an algorithm, but something more also. Around 7 years ago, a very famous computer scientist called Scott Arnson, who is now in University of Texas, that time was in MIT, had given a very important paper where he showed that finding permanent of a matrix can be, where he claimed that finding permanent of a matrix can be easily achievable by using a quantum computer. This paper has been some sort of a dispute also, but if true, then this paper has profound implications, because you know the finding permanent of an unknown matrix is actually belongs to P hash P, which is believed to be much more complicated than the NP complete problem. So if this is true, then the quantum computer, there is a actual proof that quantum computers are much more powerful than the classical computers in certain limited domains, perhaps. More important, very recently, a few computer scientists came up with a very interesting paper. And in that paper, they tried to do these complexity classes, and they came up with certain interesting results and relationships between complexity classes. Overall, this whole paper looks nothing but a standard complexity theory paper, which you see in various conferences and journals. like Folks or Stoke or TCA, maybe Journal of Theoretical Computer Science, which comes on and often. But if that calculations are true, and this happened just 2019, 2019 and 2020, if these computations are true, then at a single stroke, they proved a very important conjecture in quantum theory, disproved actually a very important conjecture in quantum theory called the Sarlson's problem, and it also disproved a very important conjecture in the in operator theory, on which I also work on. This is called the Cohn's embedding problem. The idea is that suppose if you have an infinite matrix, infinite dimensional operator, or rather say infinite matrices, can you always approximate those infinite matrices to an operational level by using just the finite matrices? The common sense tells that you can always do that thing. Even in an operational level. Operational level means that you actually have an infinite matrix, apply it upon a vector, and then see what happens. That is what the operational level I mean. And this is what the common sense tells. That is what is called as the Cohn's embedding problem, that whether it is possible or not to approximate every such operator by using just the finite level matrices. If this complexity theory paper, which has been given by the people, Thomas Videk Thomas Videk and his group, is true, then we now know that this Cohn's embedding conjecture is false. So for me as a theoretical person, this is what is the most beautiful thing I enjoy in this whole research. The theory of complexity is something which is purely in the set of computer science people. Quantum theory is kind of like physicists are applying it, and the operator theory is there, which is deep in the mathematical level. They seem totally disconnected. Okay, of course there are to and fro, because after all we need matrices, but there seem to be 2 or 3 disconnected objects. There was a problem in complexity theory, there was a problem in quantum theory, there was a problem in this operator theory. These 3 conjectures, we know that we know 10 years before that they are actually the equivalent. That is the first beauty there. They are 3 different areas, but they are all equivalent. So if one is true, then the other is true. If one is false, then the others are all false. And now there is a claim, and we still, as per the community believes that it is true, that they are actually false, and that is what the paper it tells. This is what I find in the most beautiful thing in the science, or in the most beautiful thing in what we do the research. You do one thing, you see that you throw just only one small stone, and you find out your ripples coming up from various different areas. This is what is I find the beauty in the science, and this is what I would tell everybody to think when you do research in this area. Thank you very much. Professor Panda? Yeah, questions? Hello.
Yes, sir. Thank you, sir. Sir, one question was there. What is system in quantum mechanics?
Okay, what is a system in quantum mechanics? So you have the space is the Hilbert space, and then you work with the state vectors, or the states, what we say as the matrices. Okay. So the sample space analog thing is the Hilbert space, and the probability distributions analog thing is the quantum states. So the system becomes the state itself. Okay.
Thank you, sir. Pravaran, sir, I think your doubt cleared. Any other queries? Participants, if you have any queries, kindly put in the chat box.
So I think somebody had raised his hand. Okay, so if you want if you have any other question, actually you can send me an email also. If I find time, I will definitely try to answer this. Generally, I try to answer all my emails. I will definitely try to answer it. Just mention that you have heard this lecture and so on.
Yes, sir. We will share your mail ID to them so that if they have any queries, then they will get back to you.
Sure. Or it's very simple, rb@iserbpr.ac.in, or you can see in the ISER Berhampur webpage, Maths Department, you will find out myself there.
Yes, sir. Thank you, sir. Thank you for your valuable information.
Okay, thank you. Thank you also for inviting me. Okay.
Participants, kindly fill the feedback form.
Okay, fine. So, madam, I can leave now?
Yes,
Yeah.
sir.
Okay.
Thank you, sir.
Okay.
Thank you for the wonderful session. It started with a very good introduction and all. Thank you,
Thank
sir.
you for the honor is mine, madam. Thank you very much.
Thank you, sir.
See you. Hopefully, see you again soon. Bye.
No, madam, what is the next session timing? Any
Sir,
break
12
there?
o'clock, sir.
12 o'clock. Okay, so you should announce that. Probably everybody knows. I think. Okay,
Sir?
thank you. Everybody knows about the next session timing and all. Okay.
Yes, sir. Otherwise, shall I announce now?
Yeah, please announce it. It's helpful. Even if they know, it's helpful to announce. Anyway, I'll try to join that. I will leave
Please,
now,
sir.
come to institute and then join. Okay, thank you.
Participants, as you know, like our second session will start from 12 p.m. So kindly join in time. Now we will end the meeting. Again, we will meet at 12 p.m. sir. Thank you all. That attendance form, only the feedback link, ma'am. All both are saved. Thank you all. Again, we'll meet 12 p.m. Thank you.